Okay, thank you. Good afternoon and welcome to this session on the TTEM technology. I hope I can say welcome back to a lot of you because we did this morning a session on the TTEM as we have deployed it in sub-Saharan Africa. This session will focus on the technology, and for that Pradeep Kumar, who is definitely the instrumentation wizard at Aarhus University for this technology, he will be giving the talk. My name is Paul Toft Frederiksen. I work for the Grundfos Foundation, and we work together with Aarhus University on deploying this technology for finding water where it's most needed in the last mile communities, refugee camps, host communities. Thank you. Pradeep, please.
Good afternoon, everyone. My name is Pradeep, as Paul told you. I'm postdoc working at Aarhus University. I've been working a lot with this transient TEM system. We call it TTEM for the last 3 years, and I have done my PhD. And since then, I'm working basically with the instrumentation. So in this presentation, I'm going to tell you more about the TTEM system, how the system works, about hardware, and how do we operate in the field. Next. Yeah. So this is the outline of my talk. So a little bit about motivation. Why do we need this system? Technical design of the system. What are the different components in the system, and then give you some mapping examples how well the system can map the subsurface, and then some summary. So in the near surface geophysical community, what we always wish to have a technology or a method or system that can map groundwater and can be used at the same time for geotechnical application, mapping raw materials, contaminate sources mapping, or finding the sources of contamination. What we need here is a high resolution mapping. That's something that can map few tens of meters down to 100 or 150 meters in the target where we're looking for the groundwater extraction. Then we want a system that can cover also a large area in no time. That means it should be fast enough. And then we want a system that is not too expensive, so cost efficient, so it can be deployed easily in developing countries as well. Next. So there are systems available that can do this job, what we are looking. For example, systems are built on airborne platform. We call them airborne transient electromagnetic system or frequency domain electromagnetic system. The advantages of this system, they are very fast, very effective. They can map very deep, 400, 500 meters in the ground. But the disadvantage is that they are very expensive and they usually lag in the resolution when it comes to resolving the feature in horizontal direction, or first 10, 20 meters, they lag in resolution. Next. There are ground-based systems which are very well suited what we want actually. For example, the system who can do ERT, electrical resistivity tomography, is very well established technique. People using it for many, many years. The advantage of this technology are they can resolve very well and they are well established, but the disadvantage is they are ineffective when you want to cover a larger area within a short period of time. Then, keeping that in mind, we have developed a TTEM. TTEM refers to Transient ElectroMagnetic System. So with this system, you can continuously measure while driving. This system is very effective. It can cover larger areas. When I say larger areas, I mean on a hectare scale, not on a big kilometers. It can give you very high resolution, of few 2 to 3 meters to down to 100 meters. That means it can resolve shallow and intermediate circuits. Next. I will now move to a technical design of the system, which I will explain more into detail. Go. So this is the system how it looks in the field. So the top, the image that you're seeing in the picture, the system here is ready to run in the field. The bottom is showing you the layout of the system. So you can see in the middle there is a red color frame. So this red color frame is only built for supporting a 4x2 meter a wire that we are calling here a transmitter coil, and then the whole this transmitter coil with the red design is actually built on a black sledges that you are seeing. These sledge or skis, they are used to run over the ground, and we don't have any wheel. We avoid the wheel here in order to make the system more stable. Then this 8 meter behind the system, or actually these days we are using 7 meter. This is the old picture. So behind the 8 meter of the transmitter, there is another black sledge, and which is holding a white receiver box. This is our receiver coil, and this is the coil that is recording or receiving the signal from the ground. I will explain how it works in the next. And the whole this platform, together with the receiver and transmitter, is stored by an ATV. And you can see on the top of the ATV there are yellow boxes, and these are our instruments. Here in this picture, you can see close-up looks of our instrument. So on the top left, in the top left picture, you can see there are 3 yellow boxes. There is one in the middle. We call it transmitter. This is our transmitter electronics, which has a small PC inside, together with the transmitting hardware and control boards. So this transmitter is actually connected to the receiver box, which is sitting next to it. And all these are powered by a 12-volt, 100 ampere hour battery. And this 100 ampere hour battery is enough for this system to run whole day. The system here is using a lot of power, in the sense that it's transmitting 30 ampere current, and we are repeating that measurements so fast that the system gets heat up. And in order to keep the temperature of the system below an operational limit, we have built a cooling system with the transmitter. So the cooling system is always active and trying to keep the temperature at a constant level. Yeah. So how does actually this TTEM work? This works as normally as any other TEM system. So what we do, we start transmitting current in the 4x2 loop, and then we turn off as soon as possible, and then it generates a primary magnetic field that travels into the ground, and then it induces the current into the ground, and then the strength of this current depends on what kind of material it's encountering. For example, the clay, which are very conductive, they will generate more current strength, and then in the consequence, you generate a secondary magnetic field, and this secondary magnetic field travels back to the Earth, and where we have a receiver, which is actually recording. And in the receiver, we record the strength of the secondary magnetic field as a voltage. So this is how system is running in the field. So the geometry of the system is usually fixed. So that means the center of the transmitter to distance from the center of the transmitter to the center of the receiver is fixed, and this is how it is modeled in our algorithm. And then you just have to run in a straight line. Yeah. So this is what happens when you run the system on the field. So basically what you are seeing here, the way we are running it, you think about we are scanning the ground, and it's generating the one-dimensional image at very short distances. So when you put all the 1D images together, you can look at you see the image same as the tomography. This what you see here, different colors. The blue, the different colors respond to the different strength of resistivity. The blue colors showing here your low resistive material, and this is a Danish geology, so they correspond to the clay, and and the high resistive materials, which is represented here by the red colors, they are showing you sand in this example. And all these dots that you are saying, showing you what actually depth of investigation of the system is. So, some specification about the mapping. So how fast we can run this system? We can run this system if there is a smooth field. For example, the field you are looking at the bottom of the slide, you can run 20-25 kilometers per hour without damaging the system. I mean, this is the safe limit that you can run in an open field like this. But if you have a rough terrain or a very gravel road or not very smooth, then we recommend to run 10 to 15 kilometers per hour in order to not damage the system. How often you record the data? The sampling is here is written 3 meters. That means you can record one sounding or one measurement every 3 meters. But you can 3 meters is way too many soundings if you're running whole day. So we downsample them honestly to 10 meters. So 10 meter what we can probably resolve with the system. If you're running a farm field, you can run, you can go back and forth. So you can have a line spacing between 20-25 meters. So you can cover whole area and you can create the 3D images afterwards. Coverage per day could correspond to 70 to 200 hectares per day, depending on how the fields, how large are the fields, what is the connectivity of the fields, and if the fields are very far, then you have to mobilize and demobilize the system. That might take time. Depth of investigation written here down to 100 meters, but this system can be adapted to see more than 100 meters. For example, you can put one more turn in the system. This is one turn system, but if you put one more turn, you can increase the energy and you can see, you can retrieve the late time signals and that correspond to the deeper part. So you can go 120 to 150 meters even. Yeah. Yeah, then I will show you some very nice mapping examples. Yeah, so this is one of our project area what in Aarhus University that we are working. It's in Denmark. It's called Jongil. This is 1,000 hectare area that we wanted to map, but we could not get access to all of it. So you can see all the gray colors here. They are showing where we could map, and then the red ones where we are not allowed to go due to crops or due to not getting permission from the farmers. Okay. So yeah, so I'm going to show you a profile that is running from northwest to southeast in the top. Yeah. So this is how it looks along the profile. So this is one of the very first T-term results that we got. You could see here the blue and red color. Again, blue responds to the low resistivity clay. Can you please make? Yeah, and this is how actually the interpretation should look. So the blue responds to the clay, and then you have the sand that's very dark color, red color, very high resistivity, and intermediate resistivity around 40, 50 ohm may correspond to the sand till or clay till. So you can see within 1 kilometer how much is the geology changing and where is your sand packets are if you want to drill a borehole through sand and want to extract water. So this kind of images you need. So on the top you can see how this, when I'm talking about the 3D, you can generate from the 1D images, also putting them together in 3 dimensions, you can get a 3D information which is quite nice to look at it. And yeah. So another thing about the system is that it can be easily transformed into a system that can work on lakes, rivers, and also you can use it for the shallow salt waters. We call this system FlowTem. This is just a version of TTEM. And also the system can be transformed into a system, we call it SnowTem, that works on ice, and where you can map it for example, you want to map permafrost. This is how it looks when it is in the river. So you can simply put the system on two paddle boats, and the receiver is one rubber boat, and then you can just tow behind the boat, and then it's doing exactly the same job what the TTEM is basically doing. This is our system called SnowTEM. This was designed to find a missing engine piece in Greenland. This is the layout of the system we have deployed there. But this system can be used for mapping the permafrost easily. Next. Yeah. So this is the summary of my presentation. Is the TTEM system or TTEM technology? It's actually quite versatile. It can be used on surface, water, and snow. The target, the depth is approximately 100 meters, but as I said before, it can be easily configured to see more than that. The, the most common application of the system is, of course, for finding the groundwater or surface groundwater interaction, point source contamination, mapping permafrost, and mapping the geology below the lakes and rivers and the shallow sea bottom. That's it. Thank you for listening. Hope you enjoyed the presentation.